Hello and welcome to Chapter 19. Here we study the Earth. So in the preceding chapter, in the last chapter, we learned how the solar system was formed as a byproduct of the formation of the sun. And basically what we saw there was we had the sun forming here, and then we had these swirling clouds around it. And a lot of this material or matter was pulled into the sun, but enough in the outer parts of these rings had velocities fast enough to escape the pull of the sun formation. So consequently, this swirling gas cloud remained around the sun. But in that swirling gas cloud, we had Mercury form, and then Venus, Earth, Mars, Jupiter, Saturn on out. So further away, so we have four of them that are considered the terrestrial planets, and then the rest Juniperian planets that form farther away. But the common theme between all of these is that they formed out of that swirling cloud, cloud of gas and debris. And so now that was a general overview of how the planets were formed. So now we're going to study the individual planets, and we're going to begin with our own planet and then proceed to look at all the remaining planets. So our learning goals for this chapter, we're going to be able to answer these following questions, particularly how the Earth compares to terrestrial planets with the other terrestrial planets. So Earth is one of the terrestrial planets, and then how it changed since its format, since it formed, etc. So one thing that you want to be able to do too, again, this is part of our learning goals, is compare and contrast the planets, all of them, to identify common basic principles. And when you're comparing and contrasting planets to identify commonality, that's called comparative planetology. So really, I should have capitalized that. That's a branch of astronomy, comparative planetology. So we're going to start this tour, or basically really start our exploration of the planets by studying the Earth first and its unique characteristics. So to set the stage, though, for our exploration of the Earth, I wanted to put this slide here because it is actually from your textbook. And it sets the stage really for this chapter as well as the upcoming chapters on the terrestrial planets. So the terrestrial planet, there's four terrestrial planets. So remember that it's Mercury, Venus, Earth, and Mars are the four terrestrial planets. But the title of the slide is 5 worlds, and that's because the moon is included in that. And it's our moon, the moon that's revolving around the Earth, is what we're including in this study here. So in looking at these five objects, or the 4 planets and the 1 moon, they're fascinating worlds on their own. Like each planet plus the moon, and have a lot of striking comparisons with each other, and then just a few little differences there too. So some of the comparisons, some of the similarities are Earth and Venus are actually similar in size, and that's what you can see here. You have here's Venus. Let me change my pen. Here's Venus, and then this is the Earth, and of course this is the moon. So Earth and Venus again are similar in size, but they have different atmospheres, and their surfaces are very different. But then the moon and Mercury are a lot smaller. And then Mars would fall in the middle, more of an intermediate size. So the Earth's moon has only 1/4 of the Earth's diameter. It has no atmosphere, but it's very heavily cratered. And then Earth is a water world, a lot of water covering the surface of the Earth. It's widely I don't know the statistics, how much is covered by liquid, but it's much more than half. Far more than half. And then Earth also has polar caps of solid water or ice So you have the North Pole and the South Pole, and solid water is obviously ice. And Earth, of course, has an atmosphere that's rich in water vapor, and then water droplets, which are clouds. And but then we can see too on Mars. Mars has a polar cap of frozen water, as well as carbon dioxide, but it's slightly more than half the Earth's diameter and has a very thin atmosphere. But it's very rocky and very heavily cratered. It's a little hard to tell by that picture, from what we understand of Mars, it's very rocky, cratered, a very cratered crust. The crust is the outer part of the wrapper of the planet. Volcanoes are seen on Mars, and there's also evidence of water erosion, but not a whole lot of evidence yet that there's definitive bodies of water on the planet. So then Venus, being the same size as the Earth, or very close in size, 95% of is about 95% of the diameter. So it's pretty close to being the same size. But Venus has a very thick, cloudy atmosphere that hides the surface from view. So it's very difficult to see the surface of Venus from the Earth. Most of what we know about the surface of Venus, we've seen it through Earth-based telescopes, but they're very high powered that can see through thick clouds and gases. But from what we have seen though is a very featureless surface, and it's thought that very cloudy atmosphere protects the surface from things like meteorite bombardment and cratering. But we'll get into that in a little bit. And then Mercury is slightly more than a third of the diameter of the Earth, very minimal to no atmosphere, but it's heavily cratered. So when we see how heavily cratered Mercury and the Moon are, that's why astronomers believe that Venus is not heavily cratered, because Mercury and the Moon have very little atmosphere, little to no atmosphere. But Venus has a very thick, cloudy atmosphere, much thicker and cloudier than the Earth. So that's why it's hypothesized or believed that atmosphere protects Venus from any impacts or any cratering. So to understand what all the planets are made of, the 4 terrestrial planets, we'll get into the other planet, the Jovian. We'll get into the Jovian planets later, but our terrestrial planets are differentiated into 3 separate layers. And those 3 layers are the core, the mantle, and the crust. So there's a very dense metallic core in each of the planets, and then a less dense but a very rocky mantle, that's the middle part, and then a very low density crust. So the part when we're standing on the Earth, we're standing on the crust, and it's a low density crust, and it's very easy to dig through and burrow through down to the mantle. The cratered surfaces on the planets are very old, and then the plains, like when we talk about the plains of Kansas, or pretty much any of the states, the plains are referred to as very smooth surfaces, and they're actually very young, whereas the cratered surfaces are really old. And then we have heat flowing outward from a planet, and that makes it very geologically active. And we'll get into that in more detail too. We're going to talk about that activity in the next few slides. But we want to say right here that heat flowing outward from a planet can make it very geologically active. So we know we have a lot of volcanoes and things like that, but we'll talk about that activity in a few more slides. So how do we know this? So what causes the changes in planets? And energy is actually the key to understanding those changes and understanding the nature of all the planets. So we want to follow that energy. And when we do, we see that it moves from areas of high concentration to low concentration. So that's really what produces the changes. It's that motion of energy from high concentration to low concentration. So in terms of planet formation, the interior heat, all that energy inside in the core, has to flow outward to the cooler surface. And that outward flow can create a convection current, magnetic fields, the plate tectonics, which means earthquakes. It can cause the volcanoes to erupt. So a lot of different that flow of interior heat is that flow of heat from the core out to the crust is going to create a lot of those changes that we see over time, or that we have seen over time, not just over our lifetime, but when we look back in time to discoveries of planets, 200-300 years ago to what we see today. There's changes over that relatively short amount of time too, and we could see those changes in the surface or the surface of each planet. So to look at the atmospheres now, to study the atmospheres of our planets, Mercury and the moon have negligible or little to no atmospheres, but Venus has a really thick atmosphere, and then Mars and Earth have relatively thin atmospheres. So when we look at Mercury and the moon, if you take a look at those in your textbook, I think there's some pictures. I'm sorry, it's figure 19.1, but that doesn't really help you much. But at any rate, when we look at any picture of Mercury and the moon, we can actually see the craters and then those smooth plain areas as well as the mountains. All three of those are very clearly defined. And so in order to be able to see them, that means that there's little to no atmosphere that obstructs our view. But when we look at Venus, it's completely hidden by a cloudy atmosphere. And that atmosphere is much thicker, so the clouds are much thicker than what we see on Earth. Mars, on the other hand, is a medium-sized planet with also a very thin atmosphere. So some of the questions to ponder are why do some planets have atmospheres and others do not? And we'll see in a little bit that size and temperature are both important to the creation of that atmosphere. But we want to go ahead now and start our study of the Earth as a planet, and then we'll get into more of these questions, looking at the atmospheres of each and everything. So our little postcard here gives you that breakdown of the three layers of planet Earth, but also these same three layers are in every one of our terrestrial planets. So we have a core, and what's shown here is that we have an inner core and a liquid core. So the actual core of the Earth has two layers, and the two layers of the core are the inner core and the liquid core. And then we have the mantle. That's our second or middle layer. So again, we have the core, and then we have the mantle, and then we have the crust. And the core has an inner core and a liquid core, but that still means we have three different rings or three components to our planet here. So there's four stages of any planet developing. So again, keep in mind though that the planets developed in that swirling gas cloud around the sun when the sun was forming. So our first stage of planetary development is differentiation that produced a dense core, thick mantle, and a low density crust. And then the young Earth was heavily bombarded by debris within that solar system within the creation of the solar system. So again, remember that we have our sun in the middle, and the sun is forming, and then we had these swirling gas clouds, and in those swirling clouds, we had Mercury, Venus, Earth on out. The different planets forming. So they're gobbling up. The planets are forming from all the matter in that swirling gas cloud. So when they're forming, once the planet is actually formed, there's still a lot of debris floating around there. And it hadn't been yet fully, like all of this gas cloud hadn't been fully absorbed by all the planets yet. So the young Earth, still forming, was bombarded by a lot of that debris in that swirling gas cloud. And that debris is what caused the cratering. And then, so as the Earth was continuing to form, basins then formed. So basin flooding by molten rock and later by water-filled lowlands. Water-filled lowlands came much later, but the molten rock, that's basically a lot of material coming from, like you see right here, lava or molten rock coming from the core and flowing from that high concentration to the low concentration. So this crater formed right here, and then this molten rock oozed out of the core and started filling that in, and then rain from the atmosphere added water to it. So the surface evolution is very slow, and it continues to evolve to this day due to geologic processes, one of which is erosion. So of course, when we see water and the water's flowing, it's not stagnant. It's going to erode away at the surfaces. So water erosion is one topic of evolution, and then of course, every time there's an earthquake, that changes the parameters of the Earth's crust or each of its layers. So Earth is pretty exceptional. Obviously, it's the only planet that we know of that has human life form on it. So it's definitely unusual. I mean, if you don't want to call it unique, it's definitely unusual. Here's our metric. 75% of the Earth's surface is covered by liquid water. So that is still obviously much greater than 50%. And then some of the matter on the surface of this world is actually alive. That's you and I. And of course, all the animals and bugs, plants, things like that. So, so some of the matter on the surface is actually alive and aware. But then, of course, we have a rich geology a lot of different stones, a lot of different material in general on the Earth that's not living, but that still contributes to the beauty of Earth. So the solid Earth, Earth's not really entirely solid, but nor entirely rock. So our crust floats and shifts, and it's actually on that middle layer, the mantle. That mantle is actually molten rock, and so that's a pretty thick fluid, and the crust sits on that. So because the crust sits on something that's not an entirely solid rock, that crust is going to float and shift and break apart. Float, shift, crack, break. A whole lot of activity is going to happen to that crust because it's resting on something that's not a very solid foundation. That molten rock is more like a liquid rock. And when you have the crust sitting on that, of course, it's going to keep changing and moving. The core, on the other hand, the core right at the center is, like we saw in the picture earlier, we have the very thick, dense core in the middle, right at the heart, or not in the middle, I shouldn't say, right at the heart of the or core of the Earth, and then it has that liquid around it, the liquid core as well. And that's actually a liquid metal. So we are able to explore the Earth's interior because of earthquakes. So seismic waves tell us what the pressure and the shear waves are with each earthquake. So we really depend on earthquakes to help us understand the Earth's interior. So the Earth's interior has such a high temperature and such a tremendous amount of pressure that makes exploring the Earth's interior directly impossible. So direct exploration of the core and the interior of the Earth is impossible because of the high temperature and high pressure. So even the deepest oil wells extend only a few kilometers down, and they actually don't reach through. They don't go all the way through the crust. They reach a few kilometers into the crust, but they don't actually breach the crust and go into the mantle. So it is impossible to drill far enough to sample the Earth's core. But our scientists have studied the interior through a variety of means and found clear evidence that the Earth did differentiate or does change quite a bit. So the exploration of Earth's interior is possible because earthquakes produce vibrations called seismic waves. And these waves travel through the crust and the interior and eventually register on a device called a seismograph. And there's two kinds of seismic waves that are important. That's the pressure wave and the shear wave. So the pressure wave is a lot like a sound wave, and that's because it travels in a sequence of compressions and rarefactions. Your textbook calls them compressions and decompressions. So here's your so here would be a high area of compression, and then your decompression, compression, decompression. So this is your compression, your decompression, and that's also called a rarefaction. And so our pressure waves are a lot like sound waves because they travel as a sequence of compressions and rarefactions. And as that pressure wave passes, particles of matter are going to vibrate back and forth parallel to the direction of the wave travel. So here our wave is traveling in this direction, and we're going to see the vibrations that. So every time this wave travels, the particles around the particles around here are actually going to start vibrating. So if this is air, these air molecules are going to start vibrating. The oxygen, the O2 molecules are going to start vibrating, and they're going to vibrate parallel to this direction of travel. And so those particles are going to get displaced. So when they travel back and forth parallel to the direction of the wave, so they're going to vibrate, but then they're going to start going this way too. They're going to start moving farther away, and that's actually perpendicular to this direction of travel. So the particles get displaced perpendicularly to the direction of travel, but they're going to vibrate parallel. They're going to vibrate this way, but then they're going to get displaced that way. So that means that the shear waves distort the material, but they don't compress it. Or actually, let me back up. The shear. I'm sorry. I'll make that a little more clear. So your parallel waves and your shear waves. Your pressure waves and your shear waves. So pressure waves are the compressions and decompressions, or compressions and rarefactions. And those particles vibrate back and forth parallel to the direction of the wave travel. So they're going to go back and forth this way, and that's these P waves. But these S waves, that's the one that's perpendicular. Those shear waves, the shear wave moves as displacement of particles perpendicular to the wave's direction of travel. So that means the S wave distorts the material but doesn't compress it. So there's no decompression or rarefactions with a shear wave. A normal sound wave is a pressure wave, but the vibrations that you would see like in something like Jello are actually the shear waves. So the pressure waves, because they're compressions, they can actually move through a liquid. And so that's what we see in our molten layer with those pressure waves moving through that liquid molten layer. So understanding differences in waves, if you hit a wave head on, like this one, here's your compression, and then here's your decompression, and that is going to and then here's that compression again. So this compression is going to continue to travel. But then if you hit the hammer this way, right here, if you hit it perpendicular, you're going to distort the material, and then consequently you're going to get a wave that kind of travels there's still a direction of travel, but now the material itself gets distorted. So when we look back again at our core and then our liquid core, and then the mantle, and then our crust over here, we can see that an earthquake sends these seismic waves through the Earth's interior on out to the actual crust. So how can we study something that can't be seen? Much of the natural world we actually cannot observe directly. A virus is an example. We can't actually see a virus even if we put something under a microscope. But yet scientists know enough about them to actually fight the virus by designing a vaccine. So like the influenza vaccine, that's the flu. And then obviously COVID, our COVID vaccine is on the horizon. So scientists use a lot of inferences that they chain together and then observe interactions of theory as well as evidence. So everything they could chain together about viruses helps them to deduce the structure of the structure of a virus, and then consequently, once they know the structure, they're able to design a vaccine for it. So the Earth's core is a molten metallic core, and consequently, it has a magnetic field associated with it. So that means the Earth itself has a magnetic field. And the field's a direct result of its rapid rotation plus that molten metallic core. So we have this again. We have this molten metallic core down here, but that alone doesn't necessarily create the magnetic field. We get the Earth rotating around its axis, and that makes that magnetic field swirl. So without that rotation, the magnetic field would be pretty static, nothing, maybe just only localized down here, but the spinning actually gives it this pattern where the magnetic field lines come out of the geographic north and enter into the geographic south, and they surround the Earth. It's not just two-dimensional left and right. We have this field on the top and on the bottom as well. So when we take a look a little further at this, the magnetosphere is this area. So we have our Earth right here, and then this whole big area right in here. We can still detect the Earth's magnetic region. So the magnetosphere is the region controlled by the planet's magnetic sphere. So beyond that, you really don't have, you really can't detect too much of that magnetic field. The rays of that field follow, the solar rays follow the Earth's magnetic field lines, and that's all these little purple lines coming out around here. And then these dark clouds right here are silhouetted against the much higher aurora borealis right in here. So our magnetic fields help us see things like that. So the Earth has an active crust. We've already started to talk about that in earlier slides, and now we're going to get into this much more deeply. So the plate tectonics produce much of the geologic activity on the Earth. So remember that the Earth's crust is composed of low-density rock that floats on the mantle, and the mantle is that liquid rock. So the image of a rock floating may kind of seem odd, but it's really a very dense shell, kind of like if you've ever eaten those Lindor truffle candies. It has a really soft interior, but a hard chocolate shell around it. So that's really a way to think of the planet, of Earth, where you've got this liquid or molten center or fluid-like center, but a crust around it, and that crust is going to continue to move on that liquidy mantle. So it tends to be highly plastic. The mantle rock but it's so great that sections of low density crust can actually still float on that semi-liquid mantle, much like a lily pad floating on a pond, as your textbook points out. So the motion of the crust and the erosive action of water make Earth's crust highly active. So our plate tectonics is actually the motion of the crustal plates, or the plates that the plates on the surface or the crust of the Earth. As those plates move back and forth, they give you a lot or produce a lot of the Earth's geologic activity. So the plates spread apart and can form a rift valley. Or on the ocean floor, the mid-ocean rises where the molten rock solidifies to form basalt. A plate sliding into a subduction zone can actually trigger a volcano, but a collision of two or more plates can produce a big mountain range. So chains of volcanoes like those in the Hawaiian Islands can result when plates move horizontally across a hot spot. And then continents on Earth's surface have actually moved and changed over periods of hundreds of millions of years. So the Earth's crust is in rapid motion relative to the age of the planet or the rest of the planets in the solar system. Most of our geologic features that like mountain ranges, even the Grand Canyon, are familiar outlines of actual continents and are recent products of Earth's active surface. So these tectonic plates, the average speed is pretty slow, although sudden movements do occur. Plate margins can actually stick together and accumulate stress and then release it very suddenly. And that's what happened in 2011 along a subduction zone in the Pacific Ocean off the coast of Japan. The total motion was as much as 15 meters, and the resulting earthquake caused a devastating tsunami. And a tsunami is a tidal wave. So every day, minor little earthquakes occur on moving faults, and the stress that builds in those faults that are sticking will eventually be released in a major earthquake. So a lot of little minor shifts, but then, of course, that accumulation of pressure can lead to a pretty massive earthquake. So here's actually I should have put this up a little sooner. So here's we see the subduction zones right here. Here's our subduction zones, and then here's this chain of Hawaiian Islands, and we see another subduction zone there, and of course we see all our mountain ranges as well, and our seas. But here's our mountain ranges. So just to define these subduction zones, subduction is a geologic process that happens at convergent boundaries of tectonic plates. So you're going to have two tectonic plates. So there's the boundaries, and but when they come together, when these two plates come together, if they don't come together nice and neat, pretty much stick together right there, they don't always happen. They don't always come together that way. Rather, with subduction, that's when one plate moves under another, and the plate that was forced to move under the other, that plate's forced to sink due to the high gravitational potential energy in the mantle. So we have a plate here and a plate here, and this plate here actually sinks because it sinks to the core of the Earth. So the gravitational attraction is so great that it pulls that plate down into the mantle. So there's regions where this process occurs, and those regions are the subduction zones. So that's where these subduction zones are where the plates don't come together that way. Rather, they come together where one's underneath another plate, and the one that's underneath ends up sinking. So continental drift, what I think earlier, one of the earlier slides, I mentioned that continents were moving apart, and that's really what we're showing here. So this shows right over here, oh, sorry, let me put the pen on. So right here, about 200 years ago, all the land masses on the planet, on Earth, actually were all stuck together. And so all of the continents back about 200 million years ago, all the continents had come together and formed one continent, and that one continent was called Pangaea. But then at 135 million years ago, a little more recently, we can see how all of this, all these continents right here were breaking apart and they were floating away from each other. But then 65 million years ago, we're getting some really easily discernible continents. Africa, right here, and and then South America is beginning to form. Here's America and North America, Canada. But then today, here we go from 65 million years ago to today, and here's what our planet looks like now. So we can see Florida pretty clearly formed there, but not too clear over here. And we see this part extended down into many of the South American continents. And so again, the continental drift refers to the continents drifting apart from each other more and more. And even though today, this is our view today, who knows, 65 million years from now, or even 1 million years from now, how much further apart those continents are going to spread or shift. So a billion years ago is about when the Earth formed. It was heavily bombarded by interstellar materials. Between 3 and 4 billion years ago is the furthest back that the oldest fossil can be dated to. But then pretty relatively close, we had the formation of the Grand Canyon as the most recent in our lineup here. Age of dinosaurs, the breakup of Pangaea, first animals emerged on land before the continents broke up. So our picture here is the Grand Canyon, and we can thank the breakup of Pangaea for the formation of the canyon, or I'm sorry, we can thank our plate tectonics for that. So plate tectonics pushes a byproduct of plate tectonics is that mountain ranges form, and tectonics causes little bulges in the crust as well as water erosion wearing away at the rocks. So the Colorado River began cutting through the Grand Canyon only about 10 million years ago when the Colorado Plateau warped upward under the pressure of the moving plates. It sounds like a long time ago, but not in terms of many billions of years, that we see here. So we're talking 10 million years ago, as opposed to many billions of years ago when the Earth first actually formed. So a mile down the canyon, if you went down the Grand Canyon a mile, there's rocks that are about a half a billion years old. And the roots of an earlier mountain range that stood as high as the Himalayas was discovered in the Grand Canyon region. And that was pushed up and then worn away, eroded away, and covered with sediment a very long time ago. So many of the geologic features we know on Earth have been produced by relatively recent events and activities. So now let's look at the Earth's atmosphere. So the Earth's atmosphere is key to our life on Earth. We can see without much of an atmosphere, not many of the life-sustaining chemicals would remain for us to inhale or for us to take in. It would be easy for oxygen. If we didn't have much of an atmosphere for oxygen, it would be easy for oxygen to escape the Earth's pull. So basically, the Earth's atmosphere contains a lot of life-sustaining activity. So the Earth's atmosphere is not only necessary for life, but it's also related to the crust, to the Earth's crust. The atmosphere affects the surface, or this crust. The Earth's atmosphere affects the crust through erosion by wind and water, and then in turn, the chemistry of the Earth's surface affects the composition of the atmosphere as well. So Earth originally had a primeval atmosphere from remaining gases captured during the formation of the Earth. And that atmospheric composition was severely altered, though, into a secondary atmosphere through a combination of two different processes. And those two processes are the outgassing of compounds from the Earth's interior and the bombardment of icy meteoroids and comets. So it's a common misconception that there is life on Earth because the Earth has oxygen, but in truth, oxygen was not a part of the Earth's original atmosphere. Instead, there's oxygen on Earth's atmosphere because life exists on Earth. So the photosynthesis by plants is actually what keeps a steady supply of oxygen. Photosynthesis of plants is when the plants take in the carbon and exhale the oxygen. So photosynthesis is a process used by mainly by plants, but other organisms, like paramecia, things like that. And so the plants, we'll just focus on that. But the plants convert light energy into chemical energy that can later be released to fuel the organism's activities. So the chemical energy is stored in carbohydrate molecules like sugars, and then which are then synthesized from carbon dioxide and water. So today's atmosphere, there's an ozone layer, and that's important. It's essential, and it protects the Earth's surface from ultraviolet radiation. And so here we can see all the different gases in our atmosphere. And the way this formatted here, you can see this table in your textbook right there. It's table 19.1 directly from your text. So climate and human effects on the atmosphere. Greenhouse gases are important and necessary. It protects the Earth from the harmful ultraviolet rays of the sun. But we'll see also where there's a downside to greenhouse gases. And then our picture B right here shows you the visual wavelength of sunlight coming in, and it gets scattered around. The greenhouse gas molecules actually scatter that about or deflect it back towards the Earth. And infrared radiation, too, is another source of pushing some of the sunlight directly back or holding it in the atmosphere. So misconception is that greenhouse effect is bad for the Earth. It's not bad for the Earth. It's important for the Earth because it blocks out the harmful, or it protects the Earth from the harmful ultraviolet radiation. So the truths are that the Earth has always had a greenhouse effect. That's not something new. CO2 is not the only greenhouse gas. There's other gases that are harmful to the atmosphere. And the greenhouse effect includes water vapor, methane, and other gases. That's not to say that global warming is not happening. I think we already did that assignment on global warming. But since the 20th century, temperatures have risen from 0.6 degrees Celsius to 0.9 degrees Celsius. And even though the Earth always had a greenhouse effect, human activity drastically increases the concentration of those greenhouse gases. And that's what makes the greenhouse effect harmful. These CO2 emissions and deforestation are the two biggest contributors to increasing the concentration of greenhouse gases. The Earth's albedo, or any planet's albedo, is the fraction of the sunlight hitting the actual planet that gets reflected away. So if we drew our pictures here, so if we draw Earth right here, and we'll draw the sun out here. So the Earth's albedo is the fraction of sunlight that hits the Earth and gets reflected away. So a planet with an albedo of 1 would be perfectly white, and a planet with an albedo of 0 would be perfectly black. So for the Earth, the overall albedo is 0.31 for the Earth. That's 0.31 for the Earth. So that means 31% of the sunlight that hits the Earth gets reflected back. So again, 31% of the sunlight that hits the Earth actually gets reflected back. Another misconception is the observed warming of the Earth is a result of natural causes rather than greenhouse effect. But the truth is that natural causes should actually be cooling the temperatures, not increasing them. The sun's luminosity has remained constant. So these natural causes are actually predictable changes in the Earth's axis inclination and orientation. So remember when we talked about the Milankovitch cycles, when the orientation wobbles. So we have the Earth on its axis, but that axis is going to shift a little bit to be that axis of rotation might shift back and forth, and it pulls it farther away from the sun when it shifts. So those are the natural occurrences that should actually be making the temperatures decrease. But careful observation during recent decades by space probes, the space probes are indicating that the sun's luminosity has actually remained a constant or maybe decreasing very slightly. So the observed warming must be strong to be occurring in the face of environmental effects that should be telling you that the opposite is happening. So other changes in climate are small now, and it's still a serious issue for the future, though. Even small rises in temperature will dramatically affect agriculture. And so another misconception is that all of the Earth will warm at the same rate, but that's not true because, again, that axis of rotation and then the revolution and rotation of the Earth about its axis and the sun. So truth is North America will be warm and dry while Europe actually becomes wet and cool. So our global warming is important. I don't want to downplay that, or I don't want the last few slides to be misconstrued that that global warming is not a factor. It is. We have, even though we have a normal greenhouse effect, that's natural. The heavy pollution, the creation of greater and greater amounts of carbon dioxide, human generated carbon dioxide, like emissions from cars and factories, things like that, is putting far more carbon dioxide into the atmosphere than what was originally considered a natural occurrence. So consequently, average data from 4 years in the 70s show no ozone hole, but average data from 4 years in the 90s show the rapid development of that ozone hole. So our ozone, all those greenhouse gases, that carbon dioxide, the buildup of carbon dioxide, really is puncturing a hole in our ozone layer. So, of course, if you have any questions, please feel free to reach out.